everyone. I'm presenting our work on behalf of my collaborators from UCF, Stanford University, and UC Santa Barbara. The title of our paper is Cooperative Autonomous Vehicles that Sympathize with Human Drivers. So when we think about the future of self-driving cars and their adoption to our roads and the society, this is not really the picture we can imagine: a single autonomous vehicle that's driving on a street alone without really interacting with anyone else. And this is also not the future that we can imagine, that all the vehicles that we have are autonomous and self-driving. And basically, that's kind of 100% autonomy that we have reached on the road. A realistic future mostly looks something like this, that the self-driving vehicles have to interact with human-driven vehicles, with pedestrians and others. And this brings some kind of a mixed autonomy environment. So this inspired us to think about how the interaction between these autonomous agents and the humans is going to be. How, if there's a conflict of interest between them, how are they going to solve it? Basically, this can be also expanded to any other environment that we have a bunch of robots and humans, and their utility and their interests do not necessarily match. How are we going to address these conflicts of interest? Especially in the case of driving, the group of the vehicles are trying to achieve a social goal, which is essentially having a safe and fluid traffic flow. And that's what we call as a socially desirable outcome, when everybody is driving safely and nobody's interest is being compromised. Also, one main challenge on the way to achieve these socially desirable outcomes is the fact that the humans are kind of really hard to predict, especially when we talk about their social interaction. Different humans have different social preferences, and hence they're heterogeneous in their social preference. Also, their preference is usually ambiguous and unknown. You can't really tell if a human is very egoistic, if they're very selfish, or they're selfless. There's a spectrum of humans that can be anywhere from being totally egoistic or totally selfless. So this is another challenge that we could think about when we put a bunch of autonomous vehicles or robots to interact with humans. To basically formally put these challenges, we are looking at a decision-making problem where the agents need to make local decisions in order to achieve a social goal while having partial information. While partial information, because as I said, a group of the vehicles on the road or a group of agents in this environment are humans whom their social preference is really unknown. And it's not also very homogeneous. They can have those different social preferences. So this inspired us to kind of introduce two concepts within our problem of autonomous driving in mixed autonomy environments, and basically introduce sympathy versus cooperation. Very simply talking about this, an egoistic agent is an agent that solely cares about itself, whereas a cooperative agent also cares, as well as itself, also cares about its allies, which means an autonomous vehicles which only cares about other autonomous vehicles and not necessarily the human-driven ones. Whereas if we add the sympathy component, a cooperative sympathetic vehicle now both cares about its allies, which means other autonomous vehicles, and other humans and human-driven vehicles. So keeping these two concepts of sympathy and cooperation, we can now jump and talk about what's exactly our solution. We introduced the Simco Drive platform, which is a data-driven platform based on multi-agent reinforcement learning that enables autonomous vehicles to work together, cooperate with each other, as we defined, and also sympathize with humans in order to achieve socially desirable outcomes. The start point of our solution starts with this velocity map state representation as shown in this figure, which is basically a pixel-like, it's a heat map-like representation that includes the road layout, the location of autonomous vehicles, human-driven vehicles, and also as well as a logarithmic mapping to their velocity or to their speed. Basically, this is how we encode the state information into a four-dimensional tensor and feed it to our basically system. So going forward, we decided to kind of also include some sense of time, because as you see, as you can think of, if your time steps are fairly short, the problem is not going to be very Markovian, because looking at just one, let's say, 100 millisecond ago doesn't really give a lot of information about a vehicle's trajectory. So that's why we stack 10 of these basically four-dimensional tensors, these velocity maps that I just defined, in order to somehow embed some temporal information into that, and then pass them into a 3D convolutional network to extract both spatial and temporal information, and then pass them into a flat and fully connected layer, and eventually get a probability distribution over actions at the given space, which can basically we can call it the policy, and that's what we're looking for. But just to reiterate on what we just said, this stage is being done at any agent separately, and agents are not aware of each other's decision. They are hoping that their policy will lead into socially desirable outcomes, but they don't really know if their allies are what kind of actions they're going to take. So, as you know, one of the biggest problems that multi-agent reinforcement learning solutions face is the non-stationarity of the environment. When you train multiple agents concurrently, the environment is not really stationary, because agents are evolving together. At any given step, the other agents are also being trained and they change. That's why we kind of utilize this semi-sequential Q-learning algorithm that's introduced in our paper, which means we freeze the weights of all agents and only train one for, let's say, k iteration, and then disseminate the learned policy to other agents, and keep doing this until convergence. So this showed to be very effective for the purpose of stabilizing the training process. To show you some of the results and build more intuition on our problem, let's look at this case study that we use in our paper. It's a conflictive driving scenario. It's a highway merging scenario where the interest of the merging vehicle, this vehicle -1, essentially contradicts with the interest of all other vehicles that are driving on the highway, because they want to go as fast as they can, but they also need to yield to this one in order to let it to merge. So there's kind of a conflict of interest, as we talked about before. So this human-driven vehicle, when tries to merge to the highway, they'll face a group of both human-driven and autonomous vehicles. If the autonomous vehicles are egoistic, what's going to happen is they're going to optimize for their own utility, and the merging vehicle will not be able to merge because they didn't allow it to merge, and it'll get either stuck there, or they'll cause some kind of safety critical situation. Whereas if the autonomous vehicles on the highway have both cooperation and sympathy components that we just introduced, if they're cooperative sympathetic, what's going to happen is they're going to accommodate for the merging vehicle and enable it to merge, which is what we call a socially desirable outcome. As you can see here, the guide vehicle first slows down, allows the merging vehicle to merge, and then kind of optimizes for its own local utility. And this is what we're seeking for. When we look at the sample trajectories from this merging scenario, you can see having egoistic AVs, autonomous vehicles, most of the times leads to a failed merge on the gray trajectories, whereas the orange trajectories show that cooperative sympathetic AVs show very successful performance in terms of merging. The same thing is also observable in our metrics in terms of the number of missions, the number of merges that were failed, the number of crashes, and also the average distance traveled by all vehicles, as you can see in the metrics. One might argue that the effect we saw was because we are using some kind of a deterministic model for the human-driven vehicles, and they're just simply not aggressive enough, or that they're not smart enough to merge. That's why we repeat our kind of experiments with this time, in contrast with the previous time, with an autonomous merging vehicle, as you can see. Even though the merging vehicle, being autonomous, acts more aggressively and comes up with more creative ways to merge, it still fails most of the times. And here, as you can see, although the AV merging vehicle has, you can see, a larger kind of spectrum of places that it decides to merge, it tries different things, but it still fails most of the times, as we can see. Almost 60%, 58% of the times it fails to merge and causes a crash. Although it's also trained to be basically as effective as possible in terms of merging. We also repeat our experiments with multi-lane highways, and interestingly here you can see that the vehicle number 12, the guide vehicle, kind of comes up with interesting ways. It changes lane and enables the merging vehicle to merge, and then kind of follows its own mission. So this shows the expandability of our solution, and it's kind of very interesting for us. But the main fundamental question is how much sympathy you want to add to these agents. How much should they care about others as compared to their own local utility? That's why we look at basically at two types of agents: strongly sympathetic autonomous vehicles and weakly sympathetic autonomous vehicles, and kind of look into the emerging behaviors from these two types of AVs. So let's go ahead and see how different they basically act. Firstly, starting with a weakly sympathetic AV, you can see that because here, so a sympathetic AV cares about other humans, but it also cares about others, about itself. But as we say, because it's weakly sympathetic, the weight of the agent caring about itself is more. So you can see that here, what happens is this vehicle number 12 initially slows down to basically slow down this platoon and then finally speed up. It doesn't wait for the merging vehicle to merge because it cares about itself more. Whereas strongly sympathetic agent slows down, stays slow, and makes sure the merging vehicle merges safely, and then kind of follows it to maximize its speed. So to kind of clarify, let's look at speed profiles of these two types of agents. A strongly sympathetic AV kind of slows down and stays slow, as you can see in the speed profiles, whereas the weakly sympathetic makes a hard brake and then kind of speed up. If you look at the area under the curve of these two speed profiles, obviously the weakly sympathetic has traveled a more distance because it has a bigger area under the curve, but obviously there is a safety compromise in terms of the guide vehicle not really guarding the emerging human-driven vehicle. So we kind of thought about, okay, how should we tune the social value orientation of cooperative vehicles in order to achieve socially desirable outcomes? We looked at a spectrum of all the values that we can assign to an autonomous vehicle, from purely egoistic to purely altruistic, and measured two main metrics: the number of missions that were failed and the number of episodes that had a crash. And as you can see, there is a point that can basically, between being purely egoistic or purely altruistic, that can lead to the most optimal solution. And that's how we basically tune our agents. We argue that there exists a point between pure altruism, being totally selfless, or being totally selfish, that leads to the optimal solution. Same thing is shown in the left-hand side figure, where we can tune the exact reward that we give to others as opposed to our reward to self. Thank you for your time, and please feel free to contact me or check our website for more detail.